Okay, so today I would like to talk about the theory of constraints in programming. So the theory of constraints is a theory that is not really related to programming. So in this talk there will be not much Scala and programming itself. However, I noticed that this theory of constraints is pretty useful for working with programming projects in general, since it helps you save the time. So the agenda of our today's discussion will be as follows. First of all, we will have a look at what this theory is in general and how it originated and which problems it is applicable to. And then we will have a look at the practical experience about the circumstances in which this theory can be applied, my projects that I applied it to. So what is the theory of constraints and why is it useful to for programming in general? Well, it is useful for programming in general because the theory is all about solving problems in complex environments. It was developed by Eliyahu Goldratt at the end of 20th century, and the original domain of application was manufacturing in corporate America. So basically, it appeared in the business world that had to solve its problems, like under delivery of goods, underperforming, failure to meet the market demand to their project, failure to meet deadlines, stuff like that. Eliyahu popularized his ideas about the theory of constraints in his book The Goal. It was published in 1984. And the theory of constraints itself is all about identifying the root cause of the problem at hand. So if you have some suboptimal performance at the factory, or if you fail to make profits with your business, stuff like that, then you can use the techniques from theory of constraints to analyze the root cause of the issue and find out the solution. Now, Eliyahu Goldratt, being a physicist by education, he extended this theory to be applicable not only to business systems, but to any complex system in general. And by complex system, I mean a system with large amounts of interdependencies between its components. Such systems are usually hard to analyze, and hence we need a special approach to work with these systems. The traditional approach to analysis of such systems to break them to components and understand each component by itself and then assumes that you understand the entire system, it fails in systems where interdependencies matter. You need to take into account interdependencies as well. So what is the theory of constraints? In this nice video talk that Eliyahu does, he defines the theory of constraints. He claims that the entire theory of constraints can be derived from one single word, and this word is focus. So precisely what does that mean? So he says that he defines focus as things that as doing things that need to be done and not doing things that do not need to be done. What exactly needs to be done? There is a concept called Pareto law or Pareto distribution. Basically, it is known as the 80-20 rule, and it states that 20% of your efforts yield 80% of your results. And the problem with this law is that it is applicable only to so-called linear systems. So this means that systems where the components are not interdependent, or if they are interdependent, then it is in a well-understood fashion, the fashion that you can understand. Basically, the systems that you can break into parts, analyze each part by itself, and then assumes that you understand the entire system. This law does not work for complex systems, that is, the systems with large amounts of interdependencies between components. For the complex systems, the rule becomes 99-1. So basically, 99% of your efforts do not yield any or yield very little results, and 1% of your efforts yield 99% of your output. And from this statement, if you accept this truth, it naturally follows that the local optimum of the system does not equal the global optimum of the system. So basically, if you take your complex system and well, the complex system might be your project management chain, your company, and then you assumes that if you break it into components and optimize each of the components to its very best, then you will optimize the very system to the very best. This approach will fail for the complex systems because of this 99 to 1 rule. So there is only 1% of the entire system that needs optimization. Furthermore, if you optimize the rest of the 99% of the system to its local optima, you can actually do worse to the system, because you will be not doing stuff that doesn't need to be done in the conditions where everything is interdependent. So what it means is that your actions towards the 99% that doesn't yield the result will impact actually the 1% that does yield the result. However, you will have little to no control of this impact, because you might not be able to foresee these complex dependencies. And from this information naturally follows the definition of constraint. The constraint of the system is something that prevents the system from reaching its best performance, from reaching its goal. And the constraint is precisely that 1% that needs to be worked upon to deliver 99% of the result. The theory of constraints is a prescriptive theory and that means that it actually says what to do in order to identify the constraint and solve the constraint so that the system performs better. One of the techniques, well, basically the thinking process that the theory of constraint uses to work with the constraints and to optimize the complex system that needs optimization, is the 5 focusing steps. So how it works is that first you need to identify the system constraints, and to identify the system constraints you use dedicated thinking processes that we'll cover later. After you have identified the system's constraints, you need to exploit the system's constraints. And what it means is that you need to reconfigure the system to make it perform better in terms under the conditions where you have this constraint. Next, by the way, we will see the examples of how it is done in practice, the example a bit later. And after you have made the decision to exploit the constraint, you need to subordinate everything else to this decision. And the reason for why this step is important is because the system is complex. This means that everything is interdependent in this system. It has large amount of interdependencies. This means that often it will be not possible to optimize the constraint, the module that causes the constraint on the local level. You will need the contribution of the entire system to optimize this constraint. Next, once you have tried these 3 steps, you might decide that they were not sufficient, or you need more performance from the system, and then you can make the decision to alleviate the system's constraint. This means basically solves the constraints differently than by just reconfiguring the system. This may be bringing additional resources into the system. This may be well, basically can be talking to the outside world to resolve the constraint. The 5th step is very important because the constraint will move from one component to another component. What happens is once you sufficiently optimized the constraint, it stops being the constraint. Something else becomes that 1% of the system that yields maximum output, that yields 99% of the result. And here on the slide, you see the thinking process used to identify the constraint of the system. So at the top, you see the so-called undesirable effects, or UDEs. These are the starting points of your analysis to identify what exactly causes the constraint of the system, what is the root cause of the undesirable effects. Important thing to notice is that often there will be multiple undesirable effects, but one root cause, and you should go from undesirable effects to the root cause by asking yourself the question why. So for example, the car's engine will not start. Why is that so? Because the engine needs fuel to run, and the fuel is not getting into the engine. Why is it not getting to the engine? Because there is water in the fuel pipe. Why is that? Because the car is in the swimming pool. And why is that? Because the brake doesn't work. So probably the root cause of all these undesirable effects is the faulty handbrake. But of course, first you need to get the car out of the swimming pool. Well, so it is all very nice in theory, but how exactly does that relate to programming? So here I would like to review my personal practical experience to application of this theory to programming. So the recent project that I was working on was a pretty big educational project for a security educational startup. And they basically wanted me to write 3 web applications showcasing different security vulnerabilities with correct and incorrect solutions to this vulnerabilities, so that their students can have a look and identify the correct solution to the security vulnerability in question, and among several incorrect alternatives. So basically, I had 50 security challenges to implement, scattered across 3 web applications, and well, in the format of 10, 20, 20. So one application had 20 challenges, the other 2 had 20 challenges each. And since for each security challenge I had to implement 1 incorrect branch and 3, I believe, 3 incorrect solutions to these challenges, I had 80 branches for these 20 projects, 80 Git branches, because we were working in the Git repository format. And one problem that will become relevant is that there is only one branch that is correct for the entire repository. So basically, we had to have a single branch that is immune to all the vulnerabilities, and then all of the other branches are challenge specific. So one global branch, and the rest of the branches are local to the 50 security challenges. And in this project, I noticed that the actual programming was not the most challenging part, but a number of constraints that I encountered were the most challenging part, and the solution to these constraints were not programmatic. So the constraints that I encountered, the road blockers in my process, was to make sense of, first of all, the security challenges that I am presented. So basically, what are they all about, and how would they look in the real world? How would I be able to exploit them in a real world web application? Also, I wanted to make sense of what web application do I actually need to implement, because I need to base on this web application like about 20 challenges, and to do so I need this web application to have the capabilities to do so. So for example, if I have a deserialization based challenge, I will need a web application to accept some XML. If I have, for example, encryption based challenge, so insecure cryptographic algorithm, I will need to have something with encryption there. Also, some 2 more technical challenges were to provide nice diffs while maintaining technical files in the repository. So basically, what are the diffs? Basically, the way the students are going to learn from these vulnerabilities is a multiple choice test. So basically, they are presented an incorrect vulnerable branch with the vulnerability. First, they will need to identify this vulnerability in code by marking the lines, and then to solve the vulnerability, they will be presented with 4 different alternatives, and these alternatives will be presented to them in forms of Git diffs. And hence, it is important to maintain nice and clean diffs, because people will be consuming them, then customer will be consuming that. And the technical files, such as gitignore, such as Docker files, they happen to be the clutter that my client didn't want to have. So there is a problem of this maintaining nice diffs in the conditions where I need these technical files for testing. And also there is a problem of synchronization of the branches. So as you remember, I have 1 secure branch that is global for the entire project. It is immune to all the vulnerabilities. And I have 80 of vulnerable branches that will be compared to that secure branch. And if I do not maintain this secure branch and the 80 other branches in synchronization, this will result in dirty diffs. So basically, any change that I make into the secure branch, I need it to be synchronized with all the other branches if it is unrelated to the challenges of these branches. So what solutions I found to these constraints? I also applied this. First of all, I found it really important to define the constraints in some symbolic way, either in spoken word or in writing. It is the best way to make sure that you understand the constraint and it is on the foreground of your mind. And once you have defined it, you can work with it. So for understanding-based constraints, I noticed that mind mapping works well. So architecture, challenges, all of that, I used mind maps to mind map to understand all of that. And for the two other things, for the branch synchronization and technical files management, I spent a few days to write to determine how to solve that and to write the bash scripts with the solutions. So basically no Scala programming, but that gave me the capability to not worry about things like branch synchronization and technical files management. Without that, I would have had a lot of headache while trying to meet my clients' needs, despite using some cats and purely functional programming in the code base. It would not have helped me to actually deliver the project. And this brings me to one of the points that I would like to make in this talk. It is why functional programming is not a silver bullet, I think. It's been hyping recently a lot, but I think that we need to be careful while using it, because functional programming is a solution, but a solution to which problem? And as you can see, I do not really think that we have a good understanding of the problems that are solved by functional programming, and this results in the origination of such threats, like can someone explain to me the benefits of I/O, getting about 200 comments on Reddit, and this means that people do not have the reliable source to receive this information, this very basic information of why they would use stuff like I/O monads. And also it results in such things as the monadic tutorial fallacy. It is usually when people try to answer the question of what the monad is, instead of trying to answer the question of what pains do I have that the monad might alleviate. So we have tried this approach of what the monad is, and usually it results in monadic tutorial fallacies. Nobody understands what the intuitions of other people. To solve the problem, one must define it. This is the core point of this talk. And the alternative is the solution by inertia. So if you do not define your problem, you will end up doing the things the old way, the way that you used to do things. And it is fine as long as it works. However, when it doesn't work, you need to break the inertia and use some explicit conscious techniques to find what doesn't work and how to address it. And theory of constraints is precisely the tool to use when what works in past doesn't work right now. And previously I was talking about this security project. Well, my previous approach was to implement the web applications by inertia, just sit down and code the features. However, it breaks when the project needs some management, when you need to understand the problems at hand, because there is so many of them, and also when you have some project-specific issues, such as the need to synchronize large amounts of Git branches that are interdependent, so everything depends on the security branch for the diffs. You also need some kind of conscious solution to do that. So why exactly is functional programming not a silver bullet? Well, maybe because trying to restart the engine makes little sense if you haven't pulled the car out of the swimming pool yet. So basically, the point that I'm trying to make is, before using functional programming, make sure that you understand exactly how it is going to alleviate the problem. And to begin with, you need to understand exactly what the problem is that you're trying to solve. in many cases, functional programming is actually a silver bullet because it is a very powerful technique, but not always. Well, basically, if you have any questions, you can ask them, and thank you for your attention. Okay, I guess that's it.